Tonight, we are going to walk forward in cosmic time by a number so large that no human framework can really hold it. We are going to walk 100 quadrillion years into the future of the cosmos and look around at what will be there. 100 quadrillion years. The number is 10 to the 17th power. The cosmos today is 13.8 billion years old, which is approximately 10 to the 10th power. The future moment we are traveling to is therefore approximately 7 million times older than the cosmos is now. If the entire age of the cosmos to date were compressed into a single year, the moment we are visiting tonight would be 7 million years in the future of that compressed cosmic year. There is no easy way to feel this number. Human history, from the first cities to the present, occupies approximately the last 10,000 years. The number we are walking toward is 10 trillion times longer than recorded human history. The age of complex multicellular life on Earth, approximately 500 million years, is 10 million times shorter than the cosmic time we are visiting. The age of the universe itself, the entire stretch from the Big Bang to this exact moment, is 10 million times shorter than where we are going. By the standards of cosmic time, we are walking only a small fraction of the way to the eventual heat death of the universe. The cosmos will continue to exist for far longer than 100 quadrillion years. But by every standard relevant to the cosmic objects we now observe, 100 quadrillion years is far enough into the future that the cosmos will be substantially different from what we see today. The familiar features will be gone, the remaining features will be subtle, sparse, and almost entirely composed of objects that today exist only as the dying ends of stellar evolution. Tonight, we're going to walk through what the cosmos will actually look like at this future moment. The work has been done. The detailed framework for projecting cosmic evolution into the deep future was published in 1997 by Fred Adams and Gregory Laughlin in their landmark paper, titled A Dying Universe, subsequently expanded into the book The 5 Ages of the Universe. The framework predicts specific features of the cosmos at specific future epochs, with the predictions resting on well-understood physical processes including stellar evolution, gravitational dynamics, and cosmic expansion. The predictions are not certain in their finest details, but they are reliable in their broad outline. Before we get started, sit with the basic framework. Adams and Laughlin divided cosmic history into 5 ages. The first age, called the primordial era, ended at approximately 10 to the negative 32nd second after the Big Bang, when inflation completed and the cosmos became the standard hot, dense plasma. The second age, the stelliferous era, is the era in which stars exist. We currently live in the stelliferous era. It began approximately 100 million years after the Big Bang, when the first stars ignited, and it will end approximately 100 trillion years from now, when the last star burns out. The third age, the Degenerate Era, will last from approximately 100 trillion years to approximately 10 to the 39th years, with the cosmos being populated by stellar remnants but no active stars. The fourth age, the black hole era, will last from approximately 10 to the 39th years to approximately 10 to the 100th years, with the cosmos being populated only by black holes. The fifth age, the dark era, will last from approximately 10 to the 100th years onward, with the cosmos being populated only by individual particles drifting through empty space. By the end of tonight, you're going to understand that 100 quadrillion years places us firmly within the Degenerate Era. The stelliferous era will have ended approximately 1,000 times earlier than the moment we are visiting. The black hole era will not begin for approximately 10 to the 22nd times longer than where we are. We are walking into the middle of the Degenerate Era, an epoch dominated by the cooling remnants of dead stars. Tonight, we're going to walk through 5 specific things that the cosmos will look like at 100 quadrillion years. Each one is a real prediction based on well-understood physics. Each one has implications for the broader picture of cosmic evolution. Each one connects what we observe today to what the cosmos will eventually become. The 5 things are these. The first thing is that the sky, in any sense recognizable to a human observer, will be almost completely dark. The main sequence stars that produce the visible light of the night sky today will all have died. The familiar constellations will not exist. The Milky Way will not be visible as a luminous band of stars. The cosmos will be populated in our local neighborhood only by the dim, cooling remnants of long-dead stars, with the faintest brown dwarfs and the dimmest white dwarfs being the brightest sources still emitting visible light. The second thing is that our cosmic neighborhood will be alone. The accelerating expansion of the cosmos, driven by dark energy, will have carried essentially every other galaxy and galaxy cluster beyond the cosmic event horizon. The visible cosmos, from the perspective of any observer alive at 100 quadrillion years from now, will contain only the gravitationally bound objects of what is currently called the local group, by then merged into a single massive system. Everything else will be permanently inaccessible, with its light too redshifted by the expansion to be detected. The third thing is that the remaining objects in our local cosmic neighborhood will all be stellar corpses. White dwarfs, the cooling cores of stars that exhausted their nuclear fuel. Neutron stars, the dense remnants of more massive stellar collapses. Black holes, the gravitational singularities left behind by the most massive stars. Brown dwarfs, the failed stars that never ignited proper hydrogen fusion. The local cosmic neighborhood will be a cemetery of stellar evolution products, with no active main sequence stars producing fresh starlight anywhere within the gravitationally bound region. The fourth thing is that, despite the apparent dominance of dead objects, the cosmos will still produce occasional events. Brown dwarf collisions, rare but not impossible over the enormous available timescales, will occasionally produce stellar mass objects that briefly ignite hydrogen fusion. The resulting stars, sometimes called late stelliferous stars, will burn for brief intervals before joining the cemetery population. No one expects the cosmic situation to be so layered, but it is. The cosmic dynamism will be much reduced from what we observe today, but it will not be entirely absent. The fifth thing is that the cosmos at 100 quadrillion years will be approaching, but not yet entering, the transition to the black hole era. The white dwarfs will be in the final stages of cooling toward complete thermal equilibrium with the background. The neutron stars will be largely indistinguishable from black holes in terms of their thermal emission. The black holes themselves will be slowly evaporating through Hawking radiation, though the evaporation timescales for typical stellar mass black holes are far longer than the cosmic time we are visiting tonight. The cosmos will be poised at the boundary between the era of stellar remnants and the era of pure black holes. 5 things, 5 features of the cosmos at 100 quadrillion years. By the end of tonight, you will have walked slowly through each one, with enough detail to feel the weight of the deep future, and enough perspective to see how the cosmos transitions from the active universe we observe today to the slowly winding down universe of the deep cosmic future. Pattern interrupt. The tone of tonight should not be despair. The cosmos 100 quadrillion years from now is not a sad place. It is simply a different place, with different features and different physics on display. The transitions between the eras are gradual rather than sudden, and the cosmos remains a real physical structure throughout. Whatever observers might exist at that future moment, if any do, will see a cosmos that is quieter than ours, but still genuinely cosmic. The work of imagining that future, carefully and slowly, is one of the more interesting exercises in modern cosmology. Now, let's begin with the first thing. The dark sky of the deep cosmic future. The first thing the cosmos will look like at 100 quadrillion years is dark. To understand what this actually means, we need to walk carefully through the timeline of stellar death across the stelliferous era. The current cosmic age is approximately 10 to the 10th years, or 13.8 billion years. The stelliferous era will continue for approximately 10,000 times longer than the current cosmic age. By the time we reach 100 quadrillion years, the stelliferous era will have ended approximately 1,000 times earlier than the moment we are visiting. Before we get started, sit with what follows. The stelliferous era ends because all the gas available for star formation eventually gets either incorporated into stars or pushed out of galaxies through various processes. Once the available gas is exhausted, no new stars can form. The existing stars continue to burn through their available nuclear fuel, but at progressively older cosmic ages, the rate of new star formation becomes vanishingly small. By the end of tonight, you're going to understand the specific timescales involved. The current rate of star formation in the Milky Way is approximately 1 solar mass per year, integrated across the entire galaxy. The rate is much lower than it was in the past, when the galaxy was younger and contained more available gas. The rate will continue to decrease as the gas is gradually used up. The main sequence lifetime of any given star depends on its mass, with smaller stars living much longer than larger stars. The smallest stars, with masses approximately 1/10 that of the Sun, have main sequence lifetimes of approximately 10 trillion years. By the time the cosmos reaches 100 trillion years of age, even these longest-lived stars will be approaching the ends of their nuclear-burning lives. The transition from the stelliferous era to the degenerate era is gradual. The most massive stars die first, ending their lives as supernovae and leaving behind neutron stars or black holes. The intermediate mass stars die over the subsequent billions to tens of billions of years, ending as white dwarfs after passing through the red giant phase. The lowest mass stars die last, exhausting their nuclear fuel only after many trillions of years and ending as white dwarfs without going through a dramatic red giant phase. By approximately 100 trillion years, all main sequence stars have died and the stelliferous era is over. The cosmos 100 trillion years after the present will therefore contain only the dead remnants of all the stars that have ever existed. Walking forward another factor of 1,000 to 100 quadrillion years brings us to a cosmos in which the dead remnants have been cooling for an enormous time. The white dwarfs have radiated away most of their initial heat and are at very low temperatures. The neutron stars have similarly cooled to faint thermal sources. The black holes emit only the extraordinarily faint Hawking radiation of stellar mass black holes. Pattern interrupt. The total light output of the cosmos at 100 quadrillion years will be many orders of magnitude lower than the current cosmic luminosity. Most of the remaining light will come from the cooling thermal emission of the white dwarfs, which have specific cooling timescales that depend on their masses and compositions. Typical white dwarfs cool from their initial post-formation temperatures of approximately 100,000 Kelvin to temperatures of a few thousand Kelvin over timescales of approximately 10 billion years. Continued cooling to even lower temperatures takes progressively longer, with the white dwarfs gradually approaching the temperature of the cosmic background radiation. By the time the cosmos reaches 100 quadrillion years, the cosmic background radiation will itself have cooled substantially due to the cosmic expansion. The current background temperature is approximately 2.7 Kelvin. The expansion will cool this temperature by factors of approximately 10 million by the time we reach the future epoch we are discussing. The background temperature will be in the range of approximately 10 to the negative 7th Kelvin, which is extraordinarily cold by any standard. The white dwarfs at 100 quadrillion years will have cooled to temperatures only slightly above this extremely cold background. Their thermal emission will be in the radio and microwave parts of the spectrum, with essentially no visible light produced at all. The sky, to any observer with eyes similar to ours, will appear completely dark, even when the observer is looking directly at the cooling remnants of former stars. By the end of tonight, you're going to understand that this is what we mean when we say the sky will be dark at 100 quadrillion years. The darkness is not the darkness of an empty cosmos. It is the darkness of a cosmos full of stellar remnants that have cooled below the threshold of any plausible visible light detection. The objects are still there. They just no longer produce light at wavelengths that human-style vision could see. Tonight, we're going to walk through the specific history of how the framework for understanding deep cosmic future was developed, because the Adams and Laughlin work is one of the more remarkable theoretical achievements in modern cosmology. The story begins in 1997. Fred Adams, a theoretical astrophysicist at the University of Michigan, and Gregory Laughlin, then at Lick Observatory, published a paper in Reviews of Modern Physics titled A Dying Universe. The paper was an attempt to systematically project the cosmic future across the longest available timescales using the well-understood physics of stellar evolution, gravitational dynamics, and cosmic expansion to predict what the cosmos would look like at progressively later epochs. The motivation for the work was straightforward in principle. Cosmological observations had established the basic framework of the cosmic past, with the Big Bang, the cosmic microwave background, and the subsequent evolution of structure being well documented. The cosmic past was, by the late 1990s, reasonably well understood. The cosmic future, by contrast, had received much less systematic attention. The basic physical processes that would shape the future were well known, but no comprehensive framework had been developed for thinking about what those processes would produce across the truly enormous timescales available. By the end of tonight, you're going to understand that Adams and Laughlin took on this task with substantial theoretical rigor. They worked through the timescales for stellar evolution across the full range of stellar masses, the timescales for galactic dynamics including galaxy merger and stellar ejection, the timescales for various exotic processes including proton decay and black hole evaporation, and the timescales for the cosmic expansion itself. The result was a coherent framework that divided cosmic history into 5 distinct eras, each one characterized by specific physical processes and specific dominant features. The primordial era, the first of the 5, was characterized as the period from the Big Bang until approximately 10 to the negative 32nd second, when inflation completed and the cosmos became the standard hot dense plasma. The primordial era was extraordinarily brief by cosmic standards, but contained the physics that established the basic conditions for everything that followed. Pattern interrupt. The stelliferous era, the era in which stars exist, was characterized as the period from approximately 100 million years after the Big Bang until approximately 100 trillion years. The stelliferous era includes the entire history of stellar formation, stellar evolution, and stellar death across the broad range of stellar masses. The era ends when all stars have either died or become brown dwarfs, without ever igniting proper hydrogen fusion. The Degenerate Era, the third of the five and the one we are exploring tonight, was characterized as the period from approximately 100 trillion years until approximately 10 to the 39th years. The era is dominated by the various stellar remnants we have discussed, including white dwarfs, neutron stars, brown dwarfs, and stellar mass black holes. The era ends when the various non-black hole remnants have either decayed through proton decay or been processed through gravitational dynamics, leaving only black holes as the surviving cosmic population. Now, let's begin. The black hole era, the fourth of the five, was characterized as the period from approximately 10 to the 39th years until approximately 10 to the 100th years. The era is dominated by black holes of various masses, with stellar mass black holes coexisting with the supermassive black holes that grew through accretion during the previous eras. The era ends when the various black holes have completely evaporated through Hawking radiation, with the most massive black holes lasting longest. The dark era, the fifth and final of the five, was characterized as the period from approximately 10 to the 100th years onward. The era is dominated by individual particles drifting through essentially empty space, with the cosmic structure having been completely dismantled by the various processes of the previous eras. The dark era has no well-defined end, with the cosmos continuing to exist in this state for as long as the underlying physics allows. By the end of tonight, you're going to understand why this framework was so influential. The Adams and Laughlin paper was followed in 1999 by their book, The 5 Ages of the Universe, which expanded the framework into a popular treatment accessible to a broader audience. The book became one of the more widely read works of modern cosmology, with the 5-era framework becoming a standard way to think about the deep cosmic future. The framework has been refined since its initial publication. The specific timescales for various processes have been updated as the underlying physics has been better understood. The role of dark energy, which was discovered the year after the original Adams and Laughlin paper was published, has been incorporated into the framework, with the implications for cosmic isolation and event horizons being added to the basic picture. The proton decay timescale, which determines the end of the Degenerate Era, has been refined through both theoretical work and the lack of experimental observations of proton decay in laboratory settings. The basic framework, however, has remained the standard way to think about the cosmic future. No one expects, on first thinking about cosmic eras, that the cosmic future could be projected so systematically across timescales of 10 to the 100th years or more. No one predicts that the well-understood physics of the present cosmos would yield such detailed predictions for the deep cosmic future. Absolutely no one anticipates the way the Adams and Laughlin framework has, in the decades since its publication, become a standard reference for thinking about cosmic deep time. The framework has been used as a starting point for various subsequent investigations. The role of life in the deep cosmic future has been considered by various researchers, including Freeman Dyson, who proposed specific mechanisms by which intelligent civilizations might persist into the deep, degenerate era. The role of cosmic engineering, in which advanced civilizations might modify cosmic conditions to extend their own survival, has been considered by various futurists and cosmologists. The role of the cosmic event horizon in shaping the long-term future of any specific observer has been examined in detail. Walk with me through one specific subsequent development. The discovery of dark energy in 1998, only 1 year after the original Adams and Laughlin paper, substantially changed some of the specific predictions of the framework. Before the dark energy discovery, the cosmic expansion was thought to be either slowing toward a possible recollapse or settling into a slow approach to a static, asymptotic state. Either possibility allowed the long-term cosmic structure to remain accessible to local observers indefinitely. The dark energy discovery established that the cosmic expansion is accelerating, which produces the cosmic event horizon and the eventual cosmic isolation we discussed in the second truth. The Adams and Laughlin framework was updated to incorporate this new physics, with the implications for the long-term observational possibilities being substantially modified. The basic 5-era division remained intact, but the specific picture of what observers would see at various future epochs was refined. By the end of tonight, you're going to understand that the framework, despite its theoretical rigor and its widespread acceptance, contains substantial uncertainties. The proton decay timescale is not known precisely. The Hawking radiation calculations involve some subtle physics that has not been fully tested. The behavior of dark energy over enormously long timescales is not certain. The specific predictions for individual events, particularly at the very longest timescales of the dark era, are subject to substantial revision as the underlying physics is better understood. Hold this image. The Adams and Laughlin framework was developed in 1997 as a systematic attempt to project the cosmic future across the longest available timescales. The framework has, in the decades since, become the standard reference for thinking about cosmic deep time. The 5-era division provides a coherent way to organize the various processes that will shape the cosmic future, with each era being characterized by specific physical processes and specific dominant features. The framework continues to be refined as the underlying physics is better understood, but the basic structure has remained intact since the original publication. Hold this image. The cosmos at 100 quadrillion years contains all the same objects it would have if no stars had ever existed, plus the accumulated stellar remnants from the entire stelliferous era. The remnants are dim, cold, and slowly approaching the background temperature. The sky, by any human standard of luminosity, is essentially dark. The stelliferous era will have ended approximately 1,000 times earlier than the moment we are visiting, and the cosmic environment will be dominated by the slow thermal cooling of objects that once shone brightly. The second thing the cosmos will look like at 100 quadrillion years is alone. Tonight, we're going to walk into this carefully, because the cosmic isolation that the accelerating expansion will eventually produce is one of the more striking features of the deep cosmic future. The mechanism is straightforward in principle and dramatic in consequence. The cosmos is currently expanding, with the expansion rate accelerating due to the influence of dark energy. The acceleration causes distant galaxies to recede from us at progressively higher velocities. The velocities at which galaxies recede depend on their distances, with more distant galaxies receding faster. Eventually, for any specific observer, the recession velocity of sufficiently distant galaxies exceeds the speed of light. The galaxies at greater distances than this become permanently inaccessible because no signal traveling at or below the speed of light can ever reach them. The distance at which the recession velocity equals the speed of light is called the cosmic event horizon. The horizon is currently at approximately 16 billion light-years. The horizon is shrinking in a comoving sense as the cosmic acceleration continues. Distant galaxies that are currently within the event horizon are gradually crossing outward, becoming permanently inaccessible. The trend will continue indefinitely. By the end of tonight, you're going to understand the specific timescale for cosmic isolation. The local group of galaxies which contains the Milky Way, the Andromeda Galaxy, and several dozen smaller galaxies is gravitationally bound. The gravitational binding is strong enough that the local group will not be torn apart by the cosmic expansion. The local group is therefore destined to remain a coherent system indefinitely, with its constituent galaxies orbiting their common center of mass through cosmic time. Outside the local group, however, the situation is different. The Virgo cluster, the nearest large galaxy cluster to the local group, is at a distance of approximately 50 million light-years. The Virgo cluster is not gravitationally bound to the local group. The cosmic expansion is currently carrying the Virgo cluster away from us at a speed of approximately 1,000 kilometers per second, with the speed increasing over time as the expansion accelerates. The Virgo cluster will eventually recede beyond our cosmic event horizon, becoming permanently inaccessible. Pattern interrupt. The same fate awaits every galaxy and cluster currently outside the local group. The Coma cluster, the Centaurus cluster, the Perseus-Pisces supercluster, the Shapley supercluster, and every other large structure in the cosmic web will, given enough cosmic time, cross beyond our event horizon and become permanently inaccessible. The timescales depend on the specific distances and on the cosmic acceleration rate, but the general pattern is universal. Everything beyond the gravitationally bound local group will eventually be lost. The specific timescale for cosmic isolation is approximately 150 billion years. By that future moment, the cosmos will have expanded enough that essentially all other galaxies will be beyond the event horizon. The local group will remain, but it will be all that remains visible. The cosmos beyond the local group will be inaccessible in a permanent and irreversible sense. By 100 quadrillion years, the time scale we are visiting tonight, the cosmic isolation will be complete. The local group will have merged into a single massive system, sometimes called Milkomeda in the popular literature, formed from the gradual merger of the Milky Way and Andromeda over the next several billion years and subsequent absorption of the smaller local group galaxies. Milkomeda will be a large elliptical galaxy with a mass of approximately 1 trillion solar masses. It will be, from the perspective of any observer alive at 100 quadrillion years, the entire observable universe. The view from inside Milkomeda at that future time will be of a single isolated galaxy floating in apparent emptiness. The cosmic microwave background will have cooled to the point of being undetectable. The galaxies beyond the event horizon, while they will still exist somewhere in the broader cosmos, will be permanently inaccessible. The cosmic web, with its filaments and clusters and voids, will be invisible. Any observer alive at that future moment will see only the dim remnants of stars within Milkomeda and the surrounding apparent void. By the end of tonight, you're going to understand why this is one of the more disquieting features of the deep cosmic future. The cosmos contains at present approximately 2 trillion galaxies. By the time we reach 100 quadrillion years, the number of galaxies visible to any specific observer will be 1. The reduction is from approximately 10 to the 12th galaxies down to 1 galaxy. The cosmic isolation is, in this sense, dramatic. Walk with me through what this means for the practice of astronomy at that future time. Any observers alive in Milkomeda at 100 quadrillion years would, in principle, be able to study their own galaxy in detail. They could observe the cooling white dwarfs, the slow gravitational dynamics, the rare events of brown dwarf collisions. They could measure the local properties of dark matter and dark energy, but they would have no access to any other galaxy. They would have no way to compare their local observations to observations from elsewhere. They would have no way to test cosmological theories against the broader cosmic structure. The astronomers of 100 quadrillion years from now, if they exist, would be working with a fundamentally smaller data set than we work with today. The cosmic structures we observe daily, the distant galaxies and clusters, and the cosmic microwave background would be inaccessible to them. The cosmological models they could construct, based only on observations within their own galaxy, would be substantially less rich than our current cosmological models. No one expects, on first thinking about cosmic observation, that the act of being able to see beyond one's own galaxy is itself a temporary feature of cosmic history. No one predicts that the rich observational landscape we currently enjoy will eventually be reduced to a single isolated galactic system. Absolutely no one anticipates the way the accelerating cosmic expansion is, in this sense, gradually closing the window on the broader cosmic context. The implications for the broader scientific picture are substantial. We are alive during a relatively early phase of cosmic history when the cosmos is still richly populated with observable structures. The view from our cosmic moment includes essentially all the cosmic structure that will ever be visible from this region of space. Future observers will not be able to reconstruct our current picture of the cosmos from their own observations alone. Whatever historical record we leave will be the only way for them to know about the structures we currently see. Pattern interrupt. There is something genuinely poignant about this. The cosmos we observe today is, in some sense, a temporary configuration that will not be visible to any future observer in our region of space. The richness we currently access depends on our specific cosmic moment, on our specific location in cosmic time, when the universe was still small enough that the cosmic web was within reach of our instruments. Future generations of cosmic observers, separated from us by hundreds of billions of years or more, will inherit only the local fragments. The grand cosmic picture will be permanently lost to them. By the end of tonight, you're going to understand that this fact, while genuinely strange, is not catastrophic in any practical sense. The cosmic isolation at 100 quadrillion years does not change the local physics or the local cosmic environment in any dramatic way. The objects within Milkomeda will still exist. The local dynamics will still operate. The slow processes of stellar remnant cooling will continue. Life, if it exists at that future time, will still be possible in some forms. The cosmos will simply be smaller in the observational sense than the cosmos we currently inhabit. Hold this image. By 100 quadrillion years, the cosmos will be alone in the strict observational sense. The local group will have merged into a single, isolated galaxy. The other galaxies and clusters of the cosmic web will be permanently beyond reach. The cosmic background radiation will have cooled to undetectability. The observable universe for any observer alive at that future moment will consist of one cooling galaxy floating in apparent emptiness. The cosmic richness we currently access will be a historical curiosity rather than a present reality. Before we walk into the third truth, take a slow breath here. Tonight, we're going to walk through the specific story of how the local group merges into Milkomeda, because the merger process is one of the more concrete pieces of the deep cosmic future that we can predict with substantial confidence. The basic situation is this: the Milky Way and the Andromeda Galaxy are the two largest galaxies in the local group. They are currently approximately 2.5 million light-years apart and are approaching each other at a velocity of approximately 110 kilometers per second. The approach is driven by their mutual gravitational attraction, which exceeds the cosmic expansion velocity at their separation. The two galaxies are, in this sense, gravitationally bound. The expected timeline for the merger has been calculated in considerable detail. The first close approach will occur in approximately 4 billion years from the present. At that time, the two galaxies will pass within approximately 100,000 light-years of each other, with substantial tidal effects on both systems. The first close approach will not produce a complete merger, but will substantially distort both galaxies through tidal interaction. By the end of tonight, you're going to understand that the merger process is not a single event, but a long sequence of close approaches with progressive orbital decay. The two galaxies will swing past each other, slow down through the energy lost to tidal effects, and then return for additional close approaches. The process will continue for several billion years, with the orbital separation gradually decreasing and the two galaxies becoming progressively more intermingled. Pattern interrupt. The complete merger is expected to be largely finished by approximately 7 billion years from the present. At that point, the two galaxies will have lost their distinct identities, with their stellar populations being thoroughly mixed and their dark matter halos being fully overlapping. The resulting merged system, sometimes called Milkomeda in the popular literature, will be a large elliptical galaxy with a mass of approximately 1 trillion solar masses. The merger process has substantial effects on the stellar populations of both galaxies. Stellar interactions are extremely rare during the merger because the distances between individual stars in either galaxy are enormous compared to the sizes of individual stars. But the orbital trajectories of all the stars are substantially perturbed by the changing gravitational potential. Many stars are ejected from the merger product entirely, with the ejected stars drifting into intergalactic space over subsequent cosmic time. Other stars are captured by the central regions of the merger product, contributing to the formation of a substantial central concentration. The two supermassive black holes at the centers of the two galaxies, Sagittarius A star at the center of the Milky Way and the central black hole of Andromeda, will also merge during the process. The merger of the two supermassive black holes will be the largest such event in the local cosmic neighborhood and will produce substantial gravitational wave emission. The merged central black hole will have a mass approximately equal to the sum of the original two masses, with the specific value depending on the energy lost to gravitational waves. By the end of tonight, you're going to understand that the Milkomeda system, after the merger is complete, will continue to absorb the smaller galaxies of the local group over subsequent cosmic time. The Triangulum galaxy, the third largest galaxy in the local group, will likely merge with Milkomeda within 10 to 20 billion years after the Milky Way-Andromeda merger. The various dwarf galaxies of the local group will continue to be absorbed over longer timescales, with the smallest dwarfs being absorbed last. The absorption of the smaller galaxies will continue throughout the stelliferous era. By the time stellar formation ends at approximately 100 trillion years, Milkomeda will have absorbed essentially all the original local group galaxies. The total stellar mass of Milkomeda at that time will be approximately 1 trillion solar masses, including the original masses of all the local group galaxies plus the various stars that formed within those galaxies over the intervening cosmic time. The structure of Milkomeda during its long evolution through the stelliferous and degenerate eras will gradually change. During the stelliferous era, Milkomeda will be an active galaxy producing stars at a slow but non-zero rate. As the available gas is gradually exhausted, the stellar formation rate will decrease. By the end of the stelliferous era, no new stars will be forming. During the Degenerate Era, Milkomeda will be a quiet collection of stellar remnants, with the gradual ejection of objects through gravitational dynamics being the dominant evolutionary process. No one expects, on first thinking about cosmic deep time, that the specific galaxy we currently inhabit will be substantially transformed by mergers within a few billion years. No one predicts that the cosmic perspective will be so substantially different from the Milkomeda system at any future epoch than it is from the Milky Way at present. Absolutely no one anticipates the way the cosmic future contains so much specific predictable change to our local cosmic environment. No one expects the implications, but they unfold from the basic physics. The implications for any observers alive during the Milkomeda era are substantial. The night sky from any planet in Milkomeda will look substantially different from the current night sky from Earth. The familiar constellations will have been transformed by stellar motions over billions of years. The Milky Way band of stars will not be visible, because Milkomeda is an elliptical galaxy without the disk structure that produces the Milky Way band. The Magellanic Clouds, currently visible from southern hemisphere locations on Earth, will have been absorbed into Milkomeda long before. Walk with me through what 100 quadrillion years specifically means for Milkomeda. By that time, the system will have been evolving as a merged galaxy for approximately 100 quadrillion years, minus approximately 7 billion years for the original merger and its early evolution. The system will be far older than its initial formation time. The stellar remnants will have been cooling for approximately 1,000 times the current cosmic age. The gravitational dynamics will have substantially evolved the system, with many objects having been ejected and many others having been gravitationally rearranged within the galaxy. The central supermassive black hole of Milkomeda will have grown through accretion over the cosmic time. The black hole will have absorbed various stellar remnants that have approached close to it through gravitational encounters. The mass of the central black hole at 100 quadrillion years may be approximately 10 billion solar masses or more, substantially larger than the original supermassive black holes that contributed to its formation. The takeaway is that Milkomeda at 100 quadrillion years is a real, specific physical object whose properties can be predicted with substantial confidence. The galaxy will be much older than current galaxies, much quieter than current galaxies, and much more dominated by stellar remnants than current galaxies, but it will still be a recognizable galactic structure with the same broad architecture of central concentration plus extended halo that characterizes elliptical galaxies in the modern cosmos. hold this image. Milkomeda will form from the merger of the Milky Way and Andromeda over the next several billion years. The merger product will absorb the other local group galaxies over subsequent cosmic time. The system will evolve through the rest of the stelliferous era and into the Degenerate Era. By 100 quadrillion years, the system will be a quiet elliptical galaxy populated by stellar remnants, with a substantial central supermassive black hole and an extended halo of cooling objects. The system will be the entire observable cosmos from the perspective of any observer alive at that future time. Before we continue, why this channel exists. If you have made it this far into a careful examination of cosmic deep time, you are not the casual viewer the platform expects. You are the person for whom this channel was built. Long-form cosmology, told at the pace of sleep, with the time to actually develop the slow truths of the deep cosmic future rather than collapse them into viral fragments, is not what the algorithm rewards. It is what we make anyway, because we believe the cosmos is more interesting when the questions are developed carefully. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about the cosmos. If you have already subscribed, thank you. Truly. If this is your first long-form night with the channel, welcome. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there. The audio versions are tuned for the same purpose, the same pace, the same care. Now, let us return to the data. The third thing is waiting. The third thing the cosmos will look like at 100 quadrillion years is populated entirely by stellar corpses. Tonight, we're going to walk through the specific census of what objects will remain, because the population of cosmic objects in the Degenerate Era is one of the more concrete features that the deep future cosmology framework allows us to predict. The basic situation is this. By 100 trillion years, all main sequence stars will have died. The various endpoints of stellar evolution will have produced specific populations of dead objects, each one with its own physical properties and its own characteristic lifetime. By 100 quadrillion years, these populations will have been cooling and evolving for approximately 1,000 times longer than the cosmos has existed to date, with the specific evolutionary trajectories being well understood through standard physics. The first major population is white dwarfs. White dwarfs are the cooling cores of stars that exhausted their nuclear fuel without producing a supernova explosion. The stellar mass range that produces white dwarfs as the final remnant extends from approximately 1/10 of a solar mass up to approximately 8 solar masses, which includes essentially all the stars that ever existed in the cosmos. The white dwarf population in any galaxy is therefore numerous, with the total count being approximately equal to the total number of stars that ever formed in that galaxy, minus the small fraction that ended as more exotic remnants. The point worth taking away is that the white dwarf population at 100 quadrillion years will be extraordinarily numerous. Milkomeda, the merged local group system, will contain approximately 1 trillion white dwarfs as the dominant population of stellar remnants. The white dwarfs will have masses ranging from approximately 0.5 to approximately 1.4 solar masses, with the specific distribution depending on the initial stellar populations that produced them. The white dwarfs will be cool, having radiated away most of their initial heat over the approximately 100 trillion years since the end of the stelliferous era. The cooling of white dwarfs follows specific physical laws that have been worked out in considerable detail. A typical white dwarf, immediately after its formation, has a surface temperature of approximately 100,000 Kelvin. The surface temperature decreases over time as the white dwarf radiates energy into space. The cooling rate depends on the white dwarf's mass and on its internal composition, with more massive white dwarfs cooling more slowly than less massive ones. Pattern interrupt. The detailed cooling models suggest that a typical white dwarf cools to approximately 3000 Kelvin in approximately 10 to 20 billion years. Continued cooling to approximately 1000 Kelvin takes approximately 100 billion years. Cooling to lower temperatures takes progressively longer, with the specific timescales depending on the increasingly complex internal physics of the cool white dwarf. By 100 quadrillion years, the white dwarfs will have cooled to surface temperatures of approximately 5 Kelvin or lower. They will be essentially in thermal equilibrium with the cosmic background, with the background having cooled to similar temperatures due to the cosmic expansion. The white dwarfs at this point are sometimes called black dwarfs because they emit no visible light and only the most minimal thermal radiation at very long wavelengths. The transition from white dwarf to black dwarf is gradual rather than sudden, and the term black dwarf is not always used consistently in the literature, but the basic physical state is well defined. The second major population is neutron stars. Neutron stars are the remnants of more massive stellar collapses, with initial stellar masses approximately 8 to 20 solar masses, producing neutron stars rather than white dwarfs. The neutron star population is much smaller than the white dwarf population by a factor of approximately 100, because the more massive stars are much less common than the lower mass stars that produce white dwarfs. What this means is that the specific properties of neutron stars at 100 quadrillion years, the neutron stars will have cooled to extremely low temperatures, similar to the cooled white dwarfs. The cooling timescales for neutron stars are somewhat different from white dwarfs because of the different internal physics, but the asymptotic temperatures at the cosmic moment we are visiting are similar. The neutron stars will be essentially thermal equilibrium objects at temperatures of approximately the cosmic background level. The neutron stars will continue to spin, in most cases, although the spin rates will have slowed substantially over the cosmic time. Neutron stars lose angular momentum through various mechanisms including magnetic braking and gravitational wave emission. By 100 quadrillion years, the typical neutron star will be spinning much more slowly than current pulsars, with rotation periods of hours to days rather than the millisecond to seconds of currently observed pulsars. The third major population is black holes. Black holes form from the collapse of the most massive stars, with initial stellar masses above approximately 20 solar masses producing stellar mass black holes. The black hole population is much smaller than even the neutron star population by a factor of approximately 10. The black holes have a wide range of masses, with the most massive examples in the modern cosmos being the supermassive black holes at the centers of galaxies, and the most modest examples being the stellar mass black holes formed from individual collapsed stars. Walk with me through what black holes look like at 100 quadrillion years. The black holes themselves do not cool in the same way that white dwarfs and neutron stars do. They emit Hawking radiation at a temperature inversely proportional to their mass, with stellar mass black holes emitting at temperatures of approximately 10 to the -7th Kelvin, which is essentially zero by any reasonable standard. The Hawking radiation is extraordinarily faint, and the black holes will appear essentially as dark, gravitational objects to any observer at the future epoch we are visiting. The supermassive black holes at the centers of galaxies, including the supermassive black hole at the center of Milkomeda, formed from the merger of Sagittarius A star at the center of the Milky Way and the central black hole of Andromeda, will be much larger than typical stellar mass black holes. These supermassive objects will have grown through accretion of matter during the stelliferous era and through various dynamical processes during the Degenerate Era. By 100 quadrillion years, the central supermassive black hole of Milkomeda may have a mass of approximately 1 billion solar masses or more. The fourth major population is brown dwarfs. Brown dwarfs are objects that formed like stars but did not have enough mass to ignite sustained hydrogen fusion in their cores. The mass range for brown dwarfs is approximately 0.01 to approximately 0.08 solar masses, with the lower bound being approximately 13 Jupiter masses and the upper bound being the minimum mass for stable hydrogen fusion. Brown dwarfs slowly cool by radiating away the heat from their initial gravitational contraction, but they do not undergo the dramatic energy releases of true stars. The brown dwarf population in the modern cosmos is uncertain, but is estimated to be approximately equal to the main sequence star population in numbers. The total brown dwarf population in Milkomeda is therefore expected to be approximately 1 trillion objects, comparable to the white dwarf population. The brown dwarfs at 100 quadrillion years will have cooled substantially from their formation temperatures, but will still emit faintly in the infrared at temperatures approximately 1 to several hundred Kelvin. No one expects, on first thinking about the deep cosmic future, that the cosmos will continue to be populated by such a diverse set of stellar remnants. No one predicts that the specific physics of white dwarfs, neutron stars, black holes, and brown dwarfs will produce such well-defined populations whose properties at deep future times can be calculated in detail. Absolutely no one anticipates the way the Degenerate Era cosmos retains its empirical specificity, even as the active, stellar processes that produced the original stars have long since ended. What surfaces from this is that the population of stellar corpses at 100 quadrillion years is, in a sense, more numerous than the current stellar population. Milkomeda will contain trillions of objects, each one a specific physical entity with its own history and its own future. The cosmos will be quiet but populated. The luminosity will be enormously reduced from current levels, but the inventory of cosmic objects will be substantial. Tonight, we're going to spend a longer pass on the specific physics of white dwarf cooling, because the cooling of white dwarfs is the dominant process shaping the appearance of the cosmos during the Degenerate Era, and the details are worth understanding carefully. The basic physics is this: a white dwarf, immediately after its formation from the core of a dying intermediate mass star, is extraordinarily hot. The surface temperature can exceed 100,000 Kelvin, with the central temperature being much higher. The white dwarf is supported against gravitational collapse by electron degeneracy pressure rather than by thermal pressure. The degeneracy support is essentially independent of temperature, which means that the white dwarf can lose energy through radiation without contracting further. The energy lost from the surface comes entirely from the thermal energy of the interior, and the white dwarf gradually cools as it radiates. The cooling rate depends on several specific factors. The surface temperature controls the rate of radiation, with hotter white dwarfs radiating much more energy per unit surface area than cooler white dwarfs. The internal structure controls the rate at which thermal energy can flow from the deep interior to the surface, with the relevant transport mechanisms including thermal conduction by degenerate electrons and convection in the outer layers. The composition controls the specific heat capacity, which determines how much energy must be lost to produce a given temperature decrease. What becomes clear is that the cooling of white dwarfs has been worked out in considerable detail by various theoretical groups, with the leading work being done by Leandro Althaus at the University of La Plata in Argentina, by Don Wingett at the University of Texas at Austin, and by various collaborators across the broader astrophysics community. The cooling models incorporate the various transport processes and the specific physics of the degenerate matter in the white dwarf interior. The cooling timescale at high temperatures is relatively short. A typical white dwarf cools from its initial post-formation temperature of approximately 100,000 Kelvin down to approximately 10,000 Kelvin in approximately 1 billion years. The subsequent cooling to approximately 3,000 Kelvin takes approximately 10 billion years. The cooling to lower temperatures takes progressively longer, with the temperature decrease per unit time becoming smaller as the cooling proceeds. Pattern interrupt. The reason the cooling slows down at lower temperatures is that the rate of energy radiation depends on the fourth power of the surface temperature. A white dwarf at 3000 Kelvin radiates much less energy per unit time than the same white dwarf at 10,000 Kelvin, with the rate being lower by a factor of approximately 80. The cooling timescale therefore lengthens dramatically as the temperature decreases. The detailed cooling calculations predict specific temperatures at specific cosmic times. By approximately 100 billion years after formation, a typical white dwarf will have cooled to approximately 1000 Kelvin. By approximately 1 trillion years, the temperature will be approximately 500 Kelvin. By approximately 100 trillion years, the temperature will be approximately 100 Kelvin. The cooling continues throughout the Degenerate Era at progressively slower rates. By 100 quadrillion years, the white dwarfs will have cooled to temperatures of approximately 5 Kelvin or lower. The specific value depends on the details of the cooling model and on the initial conditions of the white dwarf, but the general range is consistent across the various theoretical calculations. At these temperatures, the white dwarfs are essentially in thermal equilibrium with the cosmic background, which has cooled to similar temperatures through the cosmic expansion. The cooled white dwarfs are sometimes called black dwarfs. The term refers to the fact that they emit essentially no visible light at the very low temperatures of the deep Degenerate Era. The black dwarf nomenclature has been used since the early theoretical work on white dwarf cooling, although the specific definition of when a white dwarf becomes a black dwarf is not universally agreed upon. The basic physical state, however, is well defined as a cooled white dwarf at temperatures approaching the cosmic background. What follows from this is that no black dwarfs have ever been observed in the modern cosmos. The cooling timescales required to produce a black dwarf are far longer than the current cosmic age. The oldest white dwarfs in the Milky Way are approximately 10 billion years old and have cooled to temperatures of approximately 3000 Kelvin, which is still warm by black dwarf standards. The actual black dwarfs that will exist in the Degenerate Era have not yet had time to form in our current cosmos. Walk with me through what this implies for the empirical study of white dwarf cooling. The empirical work has been done by observing the population of white dwarfs in our galaxy and in the nearby cosmos The observed population spans a wide range of cooling ages, from very young objects that have just formed to objects approaching the maximum age allowed by the current cosmic age. The observed distribution of properties has been used to constrain the theoretical cooling models, with the agreement being generally good. The white dwarf luminosity function, which describes the number of white dwarfs at each luminosity level, provides one of the strongest empirical constraints on the cooling models. The function shows specific features at low luminosities that correspond to the cooling of white dwarfs through specific phase transitions in their interiors. The crystallization of the degenerate matter, which occurs at specific temperatures depending on the composition, produces specific features in the cooling curve that have been identified in the empirical data. No one expects, on first thinking about cosmic deep time, that the cooling of individual stellar remnants would be such an empirically rich area of research. No one predicts that the white dwarf cooling models could be tested in such detail against the observed population of white dwarfs in the modern cosmos. Absolutely no one anticipates the way the physics of cooling, while it operates over the enormous timescales of the Degenerate Era, can be empirically constrained through observations of the much shorter cooling phases accessible to current instruments. The implications for the cosmic appearance at 100 quadrillion years are substantial. The white dwarfs at that future time will be the dominant cooled stellar remnant population. Their thermal emission will be in the radio and microwave bands rather than the visible. The total luminosity of all the white dwarfs in Milkomeda will be much lower than the current luminosity of the Milky Way. But the white dwarfs will still be present, still be physically real objects, still be producing the dominant, if very faint, electromagnetic emission of the future cosmic environment. Hold this image. White dwarfs cool from initial temperatures of approximately 100,000 Kelvin to temperatures of a few Kelvin over cosmic timescales. The cooling slows dramatically as the temperature decreases, with the final approach to the cosmic background temperature taking enormously long. By 100 quadrillion years, the white dwarfs of Milkomeda will be in the final stages of their cooling, essentially in thermal equilibrium with the cosmic background. They will be physically present, but essentially invisible to any conventional observation. The cosmos will be populated by these cooled objects in numbers approaching 1 trillion, providing the dominant cosmic structure of the deep degenerate era. Hold this image. The cosmos at 100 quadrillion years is not empty. It is populated by stellar corpses in enormous numbers. White dwarfs and brown dwarfs at the trillion level, neutron stars at the 10 billion level, stellar mass black holes at the billion level, and a single central supermassive black hole orbited by the rest. The remnants are cool, the remnants are quiet, the remnants are not luminous in any sense relevant to human vision, but they are present in numbers that exceed the current stellar population of any galaxy by orders of magnitude. The fourth thing the cosmos will look like at 100 quadrillion years is, despite the dominance of dead objects, still occasionally active. Tonight, we're going to walk through the specific events that will continue to happen in the Degenerate Era, because the persistence of rare events, even in the deep cosmic future, is one of the more remarkable predictions of modern theoretical cosmology. The basic situation is this: the cosmos in the Degenerate Era is not static. The stellar remnants we discussed in the third truth continue to move, to interact, and to occasionally produce events of various kinds. The rate of events is much lower than the current cosmic rate of stellar activity, but it is not zero. Over the enormous timescales of the Degenerate Era, even very rare events become possible. The first category of rare events is brown dwarf collisions. Brown dwarfs, the failed stars we discussed in the Third Truth, occupy the same kinds of gravitational environments as proper stars. They orbit through galactic potentials, encounter each other through close passes, and occasionally undergo direct collisions. The rate of brown dwarf collisions in any given galaxy is very low, with a typical timescale for any single brown dwarf to experience a collision being approximately 10 to the 22nd years, much longer than even the cosmic age at 100 quadrillion years. Notice that this is, despite the long timescale, a relevant cosmic process. The total population of brown dwarfs in Milkomeda will be approximately 1 trillion. The rate of collisions integrated across the entire population is therefore much higher than the rate for any single brown dwarf. By the time the cosmos reaches 100 quadrillion years, the cumulative number of brown dwarf collisions in Milkomeda will be approximately 10,000, providing a substantial population of merger products. Pattern interrupt. The interesting feature of brown dwarf collisions is that the merged objects can have masses exceeding the minimum threshold for hydrogen fusion. Two brown dwarfs with masses each approximately 0.05 solar masses, if they merge, produce a combined object with mass approximately 0.1 solar masses, which is above the hydrogen burning threshold. The merged object will ignite hydrogen fusion in its core and begin to burn as a small but proper star. The resulting stars, sometimes called late stelliferous stars or brown dwarf merger stars, are small and dim by main sequence standards. They burn at low temperatures and low luminosities with effective surface temperatures of approximately 2000 Kelvin and luminosities of approximately 0.1% of solar. They are nonetheless real stars, with active hydrogen fusion producing their energy output. They are stars in a cosmos that has otherwise been entirely populated by stellar corpses for approximately 1,000 times the current cosmic age. The lifetime of these merger-produced stars is, by the standards of typical stellar lifetimes, very long. Small stars burn through their fuel slowly. A star produced by brown dwarf merger with a mass of approximately 0.1 solar masses has a main sequence lifetime of approximately 10 trillion years. The brief star in this sense is brief only relative to the enormous available cosmic time. From the perspective of any other process operating in the Degenerate Era, the merger-produced star is a substantial energy source for a substantial duration. What this picture tells us is that this is one of the more poetic features of the deep cosmic future. The cosmos in the Degenerate Era will not be entirely without active stars. Rare merger events will produce occasional new stars, each one burning for trillions of years before joining the population of cooling remnants. The cosmos at 100 quadrillion years will contain, at any given moment, a small population of these merger-produced stars actively burning hydrogen, surrounded by the much larger population of cooling corpses. The cosmos will be quiet, but not entirely silent. Now, let's begin. The second category of rare events is white dwarf mergers. White dwarfs in close binary systems can lose orbital energy through gravitational wave emission and gradually spiral toward each other. The orbital decay timescale depends on the initial orbital separation, with closer binaries decaying faster than wider binaries. The total population of white dwarf binaries that will merge over cosmic time includes essentially all the binary white dwarf systems with sufficiently close initial orbits. Walk with me through what happens when white dwarfs merge. The outcome depends sensitively on the specific masses of the merging objects. If the total mass exceeds the Chandrasekhar limit of approximately 1.4 solar masses, the merger product cannot stably exist as a white dwarf. The merger triggers either a Type Ia supernova explosion, in which the resulting object is destroyed in a thermonuclear runaway, or the collapse of the merger product into a neutron star or black hole, depending on the specific physics of the merger event. For total masses below the Chandrasekhar limit, the merger produces a single more massive white dwarf, which continues its slow thermal evolution. For total masses near or above the Chandrasekhar limit, the merger produces either a Type ER supernova or a neutron star or black hole, with the specific outcome depending on the detailed mass distribution and on the specific physics of the merger event. The rate of white dwarf mergers in Milkomeda at 100 quadrillion years will be substantially lower than the rate in the current cosmos. The closed binary populations will have largely been depleted through previous merger events. The remaining binaries will be those with the longest decay timescales, with merger events being correspondingly rare. Over the enormous available cosmic time, however, the cumulative number of white dwarf mergers will be substantial. No one expects, on first thinking about the deep cosmic future, that the cosmos will continue to produce supernova explosions at 100 quadrillion years. No one predicts that the white dwarf binary population will continue to provide the raw material for occasional Type Ia events, even when the standard stellar formation channels have long since ended. Absolutely no one anticipates the way the cosmos retains its capacity for dramatic events, even in the deep Degenerate Era. The third category of rare events is captures and disruptions by the central supermassive black hole. The supermassive black hole at the center of Milkomeda will continue to accrete matter throughout the Degenerate Era, with the accretion sources including occasional stellar remnants and dark matter on close orbits. The accretion produces tidal disruption events, in which white dwarfs or other compact objects are torn apart by the tidal field of the supermassive black hole, and the resulting debris is accreted onto the central object. Step back, and you can see that the rate of tidal disruption events at 100 quadrillion years will be very low compared to the current rate, but the events that do occur will be observable in principle to any observers alive at that future time. The disruption events produce bursts of electromagnetic radiation as the disrupted matter heats up and accretes, with the specific spectral properties depending on the masses and types of disrupted objects. The fourth category of rare events is black hole mergers. The stellar mass black holes in Milkomeda will continue to interact gravitationally, with some of them eventually merging through orbital decay and gravitational wave emission. The merger rate is very low compared to the current rate, but the events that do occur will produce dramatic gravitational wave signals that would be detectable by sufficiently sensitive detectors. Whether any such detectors will exist at 100 quadrillion years from now is, of course, an open question. Pattern interrupt. The combined effect of all these rare event types is that the cosmos at 100 quadrillion years is not static. The events are infrequent, but they are not absent. The cosmos retains a low but non-zero level of dynamism throughout the Degenerate Era. The quietness is real, but not complete. There is always something happening somewhere, even if the rate is dramatically lower than the rates we observe in the current cosmos. The empirical detection of any of these events by any observers alive at 100 quadrillion years from now would be challenging. The events are widely spaced in time and space. The instruments required to detect them would need to be sensitive across multiple wavelengths and across multiple physical phenomena. But the events are theoretically predictable, and the physics that produces them is well understood. The cosmos at the deep future time we are visiting is, in this sense, still a place where physics happens. Tonight, we're going to spend a careful pass on the physics of brown dwarf collisions, because the production of new stars through brown dwarf mergers is one of the more poetic features of the deep cosmic future, and the specific mechanism deserves careful examination. The basic situation is this. Brown dwarfs are objects with masses below the minimum threshold for sustained hydrogen fusion, typically below approximately 0.08 solar masses. They form like stars through the gravitational collapse of dense gas clouds, but they fail to reach the temperatures required for proper hydrogen fusion in their cores. Instead, they support themselves through electron degeneracy pressure and gradually cool by radiating away the heat from their initial gravitational contraction. The brown dwarf population in the modern cosmos is uncertain, but is estimated to be approximately equal to the main sequence star population in numbers. The total brown dwarf population in Milkomeda will therefore be approximately 1 trillion objects, comparable to the white dwarf population that will have accumulated by the Degenerate Era. What this leaves us with is that brown dwarfs occupy the same kinds of gravitational environments as proper stars. They orbit through galactic potentials, encounter each other through close passes, and occasionally undergo direct collisions. The rate of brown dwarf collisions in any single galaxy is very low. For any specific brown dwarf, the timescale for experiencing a collision is approximately 10 to the 22nd years, much longer than even the cosmic age at 100 quadrillion years. But the cosmic time available during the Degenerate Era is enormously long, and the brown dwarf population is enormously large. No one predicts the exact count, but the statistics are substantial. The total number of brown dwarf collisions in Milkomeda over the cosmic time up to 100 quadrillion years is approximately 10,000. The collisions are widely separated in space and time, but they occur often enough to provide a small but ongoing source of new cosmic objects. Pattern interrupt. The interesting feature of brown dwarf collisions is that the merged objects can have masses exceeding the threshold for hydrogen fusion. Consider two brown dwarfs with masses of approximately 0.05 solar masses each. If the two brown dwarfs collide and merge, the resulting object has a mass of approximately 0.1 solar masses, which is above the hydrogen-burning threshold of approximately 0.08 solar masses. The merged object will, if its interior conditions are right, ignite hydrogen fusion in its core and begin to burn as a small but proper star. The conditions required for the merged object to actually ignite fusion depend on the specific details of the collision. The collision must deposit enough energy into the merged object to raise the central temperature to the fusion ignition threshold, which is approximately 3 million Kelvin. The merged object must also retain its mass through the collision without losing too much material through the violent dynamics of the merger. The specific outcomes depend on the impact parameters, the relative velocities, and the masses of the original brown dwarfs. What emerges from this is that the merger-produced stars are small and dim by main sequence standards. They burn at low temperatures with effective surface temperatures of approximately 2000 to 3000 Kelvin. They have low luminosities, with values of approximately 0.1% of solar or less. They are nonetheless real stars, with active hydrogen fusion producing their energy output. They are stars in a cosmos that has otherwise been entirely populated by stellar corpses, for approximately 1,000 times the current cosmic age. The lifetime of the merger-produced stars is, by the standards of typical stellar lifetimes, very long. Small stars burn through their fuel very slowly. A merger-produced star with a mass of approximately 0.1 solar masses has a main sequence lifetime of approximately 10 trillion years. The brief star, in this sense, is brief only relative to the enormous available cosmic time during the Degenerate Era. From the perspective of any other process operating in the Degenerate Era, the merger-produced star is a substantial energy source for a substantial duration. The merger-produced stars eventually exhaust their nuclear fuel and become white dwarfs themselves. The final white dwarf has a mass approximately equal to the original merger product, which is somewhat larger than typical white dwarfs from single stellar evolution. The merger-produced white dwarf joins the broader population of cooling white dwarfs in Milkomeda and continues to cool over subsequent cosmic time. No one expects, on first thinking about the deep cosmic future, that the cosmos will continue to produce new stars through rare merger events long after the standard stellar formation channels have ended. No one predicts that the failed stars of the stelliferous era, the brown dwarfs that never managed to ignite proper fusion, will eventually contribute to ongoing stellar production through their collisions during the Degenerate Era. Absolutely no one anticipates the way the cosmos retains its capacity for producing genuine new stars even in the deep future, when active stellar formation has long since ended. Walk with me through what this implies for the population of active stars at 100 quadrillion years. The average rate of brown dwarf collisions in Milkomeda is approximately 10,000 events over the cosmic time we are considering. The average lifetime of the resulting merger-produced stars is approximately 10 trillion years. The expected number of active merger-produced stars at any given moment, calculated as the rate multiplied by the average lifetime divided by the total cosmic time, is approximately 10. Milkomeda, at 100 quadrillion years, will therefore contain approximately 10 active merger-produced stars at any given moment, scattered through the galaxy at locations determined by where the original collisions occurred. The contribution of these stars to the total Milkomeda luminosity is substantial, despite their small numbers. Each merger-produced star produces approximately 0.1% of solar luminosity. 10 such stars together produce approximately 1% of solar luminosity. This is much less than the current Milky Way luminosity, but is much more than the cooling white dwarf population produces in the visible band. The merger-produced stars will be, in this sense, the brightest visible sources in Milkomeda at any given moment during the deep Degenerate Era. Any observers alive in Milkomeda at 100 quadrillion years would, in principle, be able to observe these merger-produced stars. The stars would be visible at distances of perhaps a few thousand light-years through their thermal emission, with the specific detection capability, depending on the sensitivity of any available instruments. The stars would appear scattered through Milkomeda at random locations, providing the only substantial sources of visible light in the otherwise dark galaxy. The takeaway is that the merger-produced stars are, in this sense, the heroes of the deep Degenerate Era. They are the only objects continuing to produce visible light through active stellar processes. They are individually faint, but they are real stars producing real fusion energy through the same nuclear reactions that powered the original stars of the stelliferous era. The cosmic deep future contains, in this way, a continuous, if dramatically attenuated version of the stellar processes that defined the active universe. Hold this image. The cosmos at 100 quadrillion years contains, on top of the vast population of cooling stellar remnants, approximately 10 active stars produced through rare brown dwarf collisions. The stars are small, dim, and widely scattered through Milkomeda. They burn slowly, lasting for trillions of years before joining the cooling remnant population. They provide the dominant visible light of the deep Degenerate Era. They are, in this sense, the persistent embers of the cosmic stellar fire, continuing to burn long after the main combustion has ended. Hold this image. The cosmos at 100 quadrillion years contains, on top of the population of cooling stellar remnants, a slow background of rare events. Brown dwarfs occasionally collide and produce merger-driven stars. White dwarfs in close binaries occasionally merge and sometimes explode as type Ia supernovae. The central, supermassive black hole occasionally accretes a passing stellar remnant. Stellar mass black holes occasionally merge. The events are rare. The events are real. The cosmos is, despite its overall quietness, still producing physics throughout the Degenerate Era. The point worth taking away is that this is part of why the Degenerate Era is not a dead epoch. It is a slow epoch, with most of the activity being the cooling of stellar remnants over enormous timescales. But the rare events continue, providing dramatic interruptions to the general quietness. The cosmos remains a real physical system throughout the Degenerate Era, with real processes producing real events. The system is just operating at much lower intensity than the current cosmos. The fifth thing the cosmos will look like at 100 quadrillion years is poised at the boundary between the Degenerate Era and the eventual black hole era. Tonight, we're going to walk into the transition between these two ages carefully, because the long-term fate of the various stellar remnants is one of the more striking features of the deep cosmic future. The basic situation is this. The Degenerate Era, according to the Adams and Laughlin framework, will last from approximately 100 trillion years until approximately 10 to the 39th years. The era is characterized by the presence of stellar remnants, including white dwarfs, neutron stars, brown dwarfs, and stellar mass black holes in the cosmos. By the end of the Degenerate Era, the various non-black hole remnants will have either been processed through various dynamical events, or will have decayed through specific physical processes, leaving only the black holes themselves as the surviving cosmic population. 100 quadrillion years is approximately 10 to the 17th years. This is 1,000 times the current cosmic age, but only 1/1000th of the way through the Degenerate Era. The transition to the black hole era is still extraordinarily distant in time. The cosmos, at 100 quadrillion years, is, in this sense, in the early phases of the Degenerate Era rather than at its end. What this means is that the specific processes that will eventually end the Degenerate Era. The dominant process for white dwarfs and brown dwarfs is the gradual evaporation of the galactic structure. Over very long timescales, individual stars and stellar remnants are gravitationally ejected from galaxies through specific dynamical processes. The ejection mechanism involves gravitational interactions between objects of different masses, with energy being transferred from heavier objects to lighter objects in close encounters. The lighter objects gain energy and can be ejected entirely from the galaxy if their post-encounter velocities exceed the galactic escape velocity. The galaxy evaporation timescale for typical galaxies is approximately 10 to the 20th years. By that future time, the bulk of the stellar remnant population in any galaxy will have been ejected into intergalactic space, leaving only a much smaller central concentration of objects bound to the central supermassive black hole. The ejected remnants will drift through intergalactic space at low velocities, gradually being further dispersed by the cosmic expansion. Pattern interrupt. The remaining central concentration of stellar remnants will, over even longer timescales, eventually be accreted by the central supermassive black hole or ejected through gravitational interactions with the black hole. The specific time scale for the depletion of the central concentration depends on the details of the gravitational dynamics and the accretion rates, but the general process operates over approximately 10 to the 35th years. By that time, the original galactic structure will have been essentially completely dispersed, with the central supermassive black hole being the dominant surviving feature. The dominant process for stellar mass black holes is Hawking radiation. Black holes emit thermal radiation at temperatures inversely proportional to their masses, with the rate of mass loss being very slow for stellar mass objects. The total evaporation timescale for a black hole of mass approximately 1 solar mass is approximately 10 to the 67th years. Stellar mass black holes will therefore persist far beyond the moment we are visiting tonight, and far beyond even the eventual end of the Degenerate Era. The supermassive black holes will evaporate over even longer timescales, with a black hole of mass 1 billion solar masses having an evaporation timescale of approximately 10 to the 93rd years. The supermassive black hole at the center of Milkomeda will therefore persist for approximately 100 septillion times longer than the moment we are visiting tonight. The black hole era is, in this sense, dominated by the slow evaporation of the supermassive black holes that survive from the previous eras. What surfaces from this is that the cosmos at 100 quadrillion years is, despite being far from the end of the Degenerate Era, already showing some of the patterns that will eventually dominate the cosmic future. The galactic structure of Milkomeda will be more diffuse than the structure of current galaxies. The central supermassive black hole will have grown through accretion of various stellar remnants. The intergalactic space, while still bounded by the cosmic event horizon, will contain a slow accumulation of ejected remnants drifting through low-density regions. The transition to the black hole era will be gradual. The boundary between the two eras is defined by the moment when only black holes remain as significant cosmic structures. The actual transition will occur over a wide range of cosmic times, with different processes contributing at different rates. The total duration of the transition is approximately 10 to the 39th years, which is enormously longer than the moment we are visiting tonight. Walk with me through what the cosmos looks like specifically at 100 quadrillion years, given this broader framework. Milkomeda will still exist as a coherent galaxy, although with a more diffuse structure than current galaxies. The bulk of the stellar remnants will still be gravitationally bound to the galactic potential, with only a small fraction having been ejected. The central, supermassive black hole will be the largest single object, but it will not yet dominate the galactic mass budget the way it eventually will. The intergalactic space around Milkomeda will be largely empty, although it will contain some small population of objects that have been ejected from Milkomeda, or that have drifted in from formerly distant galaxies that have long since crossed beyond our cosmic event horizon. The cosmic event horizon will be at a much closer distance than the current 16 billion light-years, because the cosmic expansion will have accelerated continuously between now and the future moment. The horizon will be at approximately 1 light-year or less in co-moving distance, although the exact value depends on the specific cosmological parameters. What becomes clear is that this future moment is, in some sense, a transitional snapshot. The cosmos is past the era of active stellar formation, but not yet at the era of pure black holes. The stellar remnants are still present, but are slowly being depleted through ejection and accretion. The central, supermassive black hole is growing through accretion, but has not yet dominated the galactic mass budget. The cosmic event horizon has shrunk substantially, but the local galactic structure is still intact. No one expects, on first thinking about the deep cosmic future, that 100 quadrillion years would be a moment of genuine transition rather than a fully realized end state. No one predicts that the cosmos at this extraordinary future time would still be in the early phases of the long Degenerate Era. Absolutely no one anticipates the way the cosmic future contains so much additional history beyond even the impressive future epoch we are visiting tonight. The implications for the broader picture are substantial. The cosmos has approximately the same amount of future time available to it as it has had past time, multiplied by enormous factors. The current cosmic age is approximately 10 billion years. The eventual end of the black hole era is at approximately 10 to the 100th years. The ratio between the cosmic future and the cosmic past is therefore approximately 10 to the 90th, which is a quantity beyond ordinary human comprehension. The cosmos has, in this sense, only just begun. The vast majority of cosmic history is in the future, not the past. The features we observe today, the stars and galaxies and the cosmic web, are characteristic of a very early phase of cosmic history. The cosmos will be characterized by these features for only a tiny fraction of its eventual total duration. The Degenerate Era, the Black Hole Era, and the Dark Era will together occupy enormously more time than the Stelliferous Era will have. We are alive during the brief opening act of an enormously long cosmic story. Mark this moment. There is something genuinely strange about this. The cosmos we observe is, in a precise sense, atypical relative to the cosmos that will exist for most of cosmic time. The conditions that allow stars to exist, that allow planets to form, that allow life to develop, are characteristic of only a small fraction of cosmic history. For most of cosmic time, the cosmos will be a quieter and emptier place than the cosmos we currently observe. What follows from this is that this is, in some sense, the deepest implication of the deep cosmic future. The vast majority of cosmic history will be characterized by configurations very different from the current configuration. The cosmos we observe is genuinely early. The cosmos that will eventually dominate the total cosmic story is the slowly evolving cosmos of the deep future, with its stellar remnants and its accumulating black holes and its eventual approach to the Dark Era. Tonight, we're going to spend a careful pass on the specific physics of Hawking radiation and black hole evaporation, because the eventual decay of black holes through this process is what ends the black hole era, and the timescales involved are extraordinarily long. The basic physics is this. In 1974, Stephen Hawking demonstrated through a careful theoretical calculation that black holes are not actually completely black. They emit thermal radiation, called Hawking radiation, from their event horizons. The radiation has a specific temperature that depends on the black hole's mass, with smaller black holes emitting at higher temperatures and larger black holes emitting at lower temperatures. The specific temperature is given by the Hawking formula. For a black hole of mass equal to the Sun, the Hawking temperature is approximately 10 to the negative 7th Kelvin. For a black hole of mass 1 billion solar masses, like the supermassive black hole at the center of Milkomeda, the temperature is approximately 10 to the negative 16th Kelvin. The temperatures are extraordinarily low for any stellar mass or supermassive black holes far below the temperature of the cosmic background radiation in the current cosmos. Notice that the low temperatures have implications for whether black holes are net emitters or net absorbers of radiation in the current cosmos. A black hole at a temperature lower than the surrounding cosmic background absorbs more radiation from the background than it emits through Hawking radiation. In the current cosmos, all stellar mass and supermassive black holes are therefore net absorbers, gaining mass slowly from the cosmic background. The situation changes as the cosmic background temperature decreases due to the cosmic expansion. The current background temperature is approximately 2.7 Kelvin. The expansion will cool this temperature substantially over cosmic time, with specific values depending on the cosmological parameters. By approximately 10 to the 15th years from now, the background temperature will have decreased to approximately 10 to the negative 10th Kelvin, which is still much higher than the Hawking temperature of any stellar mass black hole. Pause and notice. The crossover at which stellar mass black holes become net emitters happens at approximately 10 to the 24th years from now, when the cosmic background temperature has decreased below the Hawking temperature of typical stellar mass black holes. At that point, the black holes begin to slowly lose mass through Hawking radiation. The mass loss is extraordinarily slow at first, with the rate increasing as the black hole shrinks and its temperature increases. By 100 quadrillion years, the timescale we are visiting tonight, the cosmic background temperature will have decreased to approximately 10 to the negative 7th Kelvin or lower, which is approaching the Hawking temperature of stellar mass black holes. The black holes will be, by that future epoch, beginning to enter the regime where they are net emitters rather than net absorbers. The transition is gradual rather than sudden, and the specific timescales depend on the detailed cosmological evolution. The total evaporation time for a stellar mass black hole through Hawking radiation is approximately 10 to the 67th years. This is enormously longer than 100 quadrillion years. The black holes at 100 quadrillion years are therefore essentially unchanged from their initial post-formation masses, despite being on the verge of becoming net emitters. The slow Hawking emission has not yet substantially affected their mass budgets. The supermassive black holes have even longer evaporation times. The supermassive black hole at the center of Milkomeda, with a mass of approximately 1 billion solar masses, has an evaporation time of approximately 10 to the 93rd years. This is enormously longer than the eventual end of the black hole era at approximately 10 to the 100th years. The supermassive black holes are, in this sense, the longest-lived structures in the entire cosmic future, persisting essentially unchanged through enormously long stretches of cosmic time. What this picture tells us is that the eventual evaporation of black holes is, despite happening on extraordinarily long timescales, a real physical process with specific predicted properties. The final stages of black hole evaporation are particularly dramatic. As a black hole's mass decreases, its Hawking temperature increases. The rate of mass loss therefore accelerates, with the final stages being explosive rather than gradual. The last second of any black hole's existence releases approximately 10 to the 35th ergs of energy, equivalent to a small supernova explosion. The energy released in the final stages of black hole evaporation has been considered by various researchers as a possible source of observable signatures in the deep cosmic future. Whether any such signatures would be detectable depends on the specific cosmic conditions at the time of the explosions and on the sensitivity of any available instruments. The empirical detection of black hole evaporation events is, in any case, far in the future and is not relevant to the current observational picture. Walk with me through one specific implication. The supermassive black hole at the center of Milkomeda will, at 100 quadrillion years, still be essentially unchanged from its initial post-merger mass. The black hole will have grown through accretion of various stellar remnants over the cosmic time, but the Hawking emission will not have produced any significant mass loss. The black hole will continue to exist for approximately 10 to the 93rd years from the present, which is approximately 10 to the 76th times longer than 100 quadrillion years. By the standards of the supermassive black hole's eventual evaporation timescale, the moment we are visiting tonight is essentially the beginning of its history. No one expects, on first thinking about black hole evolution, that the eventual evaporation of supermassive black holes would happen on such extraordinarily long timescales. No one predicts that the cosmic future contains so much additional history beyond even the impressive future epoch we are visiting tonight. Absolutely no one anticipates the way the Hawking radiation physics produces such specific predictions for the final fate of all the black holes in the cosmos. The implications for the broader picture of cosmic deep time are substantial. The black holes are the longest-lived structures in the entire cosmic future. They persist through the Degenerate Era, throughout the black hole era, and only finally evaporate in the very late stages. The cosmic story, after the various processes of the Degenerate Era have dispersed the stellar remnants, and after the central supermassive black holes have absorbed the central concentrations, will be dominated for enormously long times by the slow evaporation of black holes through Hawking radiation. The dark era, which begins after all the black holes have evaporated, will be characterized by individual particles drifting through essentially empty space. No one predicts the specific outcome, but the broad pattern is consistent. The cosmic structure will have been completely dismantled. The cosmic time available for this final era is, in principle, unbounded, with the cosmos continuing to exist in this state for as long as the underlying physics allows. Hold this image. Black holes evaporate through Hawking radiation on extraordinarily long timescales. Stellar mass black holes evaporate over approximately 10 to the 67th years. Supermassive black holes evaporate over approximately 10 to the 93rd years. At 100 quadrillion years, the time scale we have explored tonight, the black holes are essentially unchanged from their initial post-formation masses. The evaporation is just beginning. The vast majority of cosmic future history involves the slow evaporation of black holes that are still essentially intact at the moment we have visited. Hold this image. The cosmos at 100 quadrillion years is poised at an early phase of the Degenerate Era, with the transition to the black hole era still extraordinarily far in the future. The cosmos is alone dark, populated by stellar corpses, occasionally active through rare events, and slowly evolving toward its long-term fate. The future moment we have visited tonight is, in this sense, both extraordinarily distant from our current epoch and still extraordinarily early relative to the eventual cosmic future. The full cosmic story extends enormously farther than even the impressive timescale we have explored. Tonight, we're going to spend a careful pass on what the deep cosmic future implies for the broader picture of cosmic time, because the implications go beyond the specific physical predictions and touch on how we should think about cosmic timescales more generally. Before we get started, sit with the basic temporal scope. The cosmos is currently approximately 10 to the 10th years old. The stelliferous era will continue for approximately 10 to the 14th years, which is 10,000 times the current cosmic age. The Degenerate Era will last from then until approximately 10 to the 39th years. The Black Hole Era will continue until approximately 10 to the 100th years. The Dark Era has no defined end. The total cosmic future is, in this sense, enormously longer than the cosmic past. The ratio between the cosmic future and the cosmic past is approximately 10 to the 90th or more. This is a quantity beyond ordinary human comprehension. We are alive, in this sense, at a remarkably early phase of cosmic history. Almost all of cosmic time is in the future, not the past. The features we observe today, the active stellar populations and the rich cosmic web, are characteristic of only a tiny fraction of cosmic history. The vast majority of cosmic time will be characterized by configurations we are exploring tonight, or by even more distant future configurations. Step back, and you can see that this implies something specific about our cosmic moment. We are alive during the brief early phase of an enormously long cosmic story. The conditions that allow stars to exist, that allow planets to form, that allow biology to develop, are characteristic of only the small fraction of cosmic time that constitutes the stelliferous era. Once that era ends, the cosmos will become much quieter, with the various long stretches of the degenerate, black hole, and dark eras playing out across timescales that dwarf the cosmic past. Linger here. The implications for the question of where biological life fits in the cosmic story are interesting. The conditions for life as we know it require active stellar processes. Stars provide the energy that powers planetary biospheres. The end of the stelliferous era will therefore mean the end of any life that depends on stellar energy. Whatever observers might exist after the end of the stelliferous era would need to operate on dramatically different energy budgets than current biological life uses. Some theoretical work has considered the possibility of life persisting into the deep cosmic future. The physicist Freeman Dyson proposed in 1979 that intelligent civilizations might be able to extend their survival into the degenerate era by progressively slowing down their metabolic processes to match the dramatically reduced energy availability of the future cosmos. Dyson's calculations suggested that suitable intelligence might persist indefinitely, in principle, with subjective experience being preserved, despite the enormous slowdown relative to objective cosmic time. The Dyson proposal has been substantially refined and debated since its original publication. Various researchers have considered the specific energy sources available during the degenerate era, including the cooling thermal radiation of stellar remnants and the rare events of brown dwarf collisions and other dynamical processes. The energy budgets are very tight, but the calculations suggest that careful management of energy resources could in principle allow some form of intelligent activity to persist for substantial periods. The implications of the cosmic event horizon for any persistent civilization are substantial. The civilization would be limited to the local cosmic neighborhood, namely the gravitationally bound system of Milkomeda. The civilization could not, in principle, expand beyond the local system, because the cosmic expansion would have carried all other regions beyond reach. The civilization would be permanently isolated, with no possibility of communication or contact with any other civilization that might have arisen elsewhere. What this leaves us with is that the deep cosmic future, considered carefully, has substantial implications for how we should think about the meaning of any specific cosmic moment. The current cosmic moment is genuinely valuable in being part of the rich early phase of cosmic history. The future cosmic moments will be characterized by progressively less observational richness and progressively more challenging conditions for the kind of life and intelligence that currently exists. There is something genuinely strange about being alive at this specific moment in cosmic history. The cosmos has, in a precise sense, given us a particularly rich epoch to observe. The stars are still burning. The galaxies are still active. The cosmic web is still mappable. The cosmic background radiation is still measurable. The full cosmic structure is, by every available indication, still accessible to our instruments and our methods. Future generations of observers, if any exist at progressively later cosmic times, will inherit progressively less rich observational situations. No one expects, on first thinking about cosmic time, that being alive at a specific moment in cosmic history would have such measurable implications for what observational picture is available to us. No one predicts that the current cosmic moment would be so privileged in terms of observational richness compared to the deep cosmic future. Absolutely no one anticipates the way the cosmic deep future is genuinely emptier, by every available measurement, than the cosmos we currently observe. Expectation? Cosmic observation will continue to improve indefinitely as instruments become more sensitive. Reality. Cosmic observation has a peak window, and we are alive within that window. Future generations will inherit a much emptier cosmos than the cosmos we currently inhabit, regardless of how good their instruments become. Walk with me through the philosophical implications. The current cosmic moment is, in this sense, a kind of privileged time for observation. The privilege is not absolute. The cosmos is what it is, regardless of who is observing it. But the observational situation we currently enjoy is genuinely better than the observational situations that will be available at the future cosmic moments we have explored tonight. The cosmos of 100 quadrillion years will contain less observable structure, less cosmic background information, and less accessible richness than the current cosmos contains. This has implications for how we might think about the value of contemporary cosmological work. The empirical observations being made by the current generation of cosmologists, including the James Webb Space Telescope observations of the first galaxies and the Planck satellite observations of the cosmic microwave background and the various large surveys of cosmic structure, are observations of a configuration that will not be available to any future observer in our region of space. The work is, in this sense, more time-sensitive than ordinary scientific work. The observations being made now are observations of a temporarily accessible cosmos, with the temporary accessibility being a feature of cosmic time itself. What emerges from this is that this is, in some sense, the most personal implication of the deep cosmic future. The cosmos has given us a particular moment to observe. The moment is rich. The moment is empirically productive. The moment will not last forever. Future cosmologists, if any exist at substantially later cosmic times, will work with a much smaller data set than we have available. The empirical contributions being made now have a particular cosmic value that future contributions will not have. Hold this image. We are alive during the early observational phase of an enormously long cosmic story. The current cosmic moment is empirically rich in ways that the deep cosmic future will not be. The vast majority of cosmic time will be characterized by configurations we have explored tonight, or by even more distant future configurations, with progressively less observational richness available to any observers alive at those times. The current moment is, in this respect, both genuinely privileged and genuinely transient. Tonight, we're going to address 5 common misconceptions about the deep cosmic future directly, because each one is widely repeated in popular discussion, and each one deserves a careful correction. Now, let's begin with the first misconception. The misconception is that the deep cosmic future is purely speculative. The claim sometimes appears in skeptical contexts that suggest the predictions are guesswork rather than rigorous physics. The technical reality is that the deep cosmic future predictions rest on extremely well-established physics. Stellar evolution timescales are calculated from nuclear physics and stellar structure models that have been extensively tested against current stellar populations. Galaxy merger timescales are calculated from gravitational dynamics that have been tested in many empirical contexts. Hawking radiation timescales are calculated from quantum field theory in curved spacetime, with the theoretical framework being well established despite the lack of direct empirical detection. No one expects, on first hearing the skeptical framing, that the gap between the popular skepticism and the technical situation could be quite this large. No one predicts that predictions for cosmic timescales of 10 to the 100th years could rest on such well-established physics. Absolutely no one anticipates the way the deep cosmic future framework has, through decades of refinement, become one of the more theoretically rigorous areas of modern cosmology. Before we get started on the second misconception, sit with why the first one persists. The timescales involved are so far beyond human experience that the predictions can feel like science fiction. The actual underlying physics, however, is the same physics that successfully describes current cosmic phenomena. The reliability of the predictions follows from the reliability of the underlying physics. Now, let's begin with the second misconception. The misconception is that the deep cosmic future is uniformly dark and dead. The claim sometimes appears in popular contexts that present the future cosmos as a featureless void. The technical reality is more nuanced. The deep cosmic future is much quieter than the current cosmos, but it is not entirely featureless. Stellar remnants continue to cool and emit faint radiation. Rare events, including brown dwarf collisions and white dwarf mergers, continue to occur. The cosmos retains its structure, even if the structure is less obvious to any potential observer than the current cosmic structure. The takeaway is that this is part of why the deep cosmic future is more interesting than the popular framing suggests. The cosmos at 100 quadrillion years is genuinely quiet by current standards, but is not the empty void that some popular discussions imply. The cosmos retains specific empirical content throughout the Degenerate Era, with the content being detectable by sufficiently sensitive instruments, if any such instruments exist, at that future time. The third misconception is that the deep cosmic future is irrelevant to current concerns. The claim sometimes appears in dismissive contexts that suggest cosmic deep time has no bearing on present matters. The technical reality is that the deep cosmic future provides crucial context for thinking about the meaning of current cosmic observations. The current cosmic moment is a temporary configuration in a much longer cosmic story. The observations being made now are observations of a particularly rich phase that future observers will not be able to reproduce. The deep cosmic future therefore provides important perspective on the value of current empirical work. Expectation: cosmic deep time is irrelevant to current concerns. Reality: cosmic deep time provides crucial context for understanding the value and the limits of current cosmic observations. The fourth misconception is that the deep cosmic future predictions are immune to revision. The claim sometimes appears in confident contexts that present the Adams and Laughlin framework as the final word on cosmic future. The technical reality is more measured. The framework continues to be refined as the underlying physics is better understood. The role of dark energy was added to the framework after the original publication. The specific timescales for various processes have been updated as better calculations have become available. The basic 5-era structure has remained intact, but the details continue to evolve. No one predicts, on first encountering deep cosmic future cosmology, that the framework would be subject to ongoing refinement after decades of theoretical work. No one expects that the specific predictions, while broadly reliable, could continue to evolve as understanding improves. Absolutely no one anticipates the way the deep cosmic future framework combines theoretical rigor with ongoing refinement in this specific way, a slow turn. The fifth misconception is that the deep cosmic future has been fully worked out at all timescales. The claim sometimes appears in confident discussions that present the cosmic future as a closed topic. The technical reality is that substantial open questions remain. The behavior of dark energy over enormously long timescales is not certain. The proton decay timescale, which determines the end of the Degenerate Era, is poorly constrained. The detailed physics of the very late stages of black hole evaporation involves quantum gravity effects that have not been fully worked out. The field remains, in this sense, theoretically active. The point worth taking away is that this is part of why the deep cosmic future continues to be an interesting research area. The combination of well-established broad predictions with substantial open questions about specific details has produced an active theoretical community working on various aspects of cosmic deep time. The work continues with substantial refinement expected over the coming years. Hold this image. 5 misconceptions, each one widely repeated, each one wrong in specific ways. The corrections do not diminish the significance of the deep cosmic future as a research topic. The future is genuinely strange. The future is genuinely far from current conditions. The future implications for cosmic life and observation are genuinely substantial, but the popular framings, while attention-grabbing, do not accurately represent the technical situation. Expectation: the popular framing. Reality: the actual situation is more measured, more interesting, and in some ways more honest than any of the popular framings suggest. What this leaves us with is a clearer view of what the deep cosmic future actually means. Not pure speculation, not uniform emptiness, not irrelevant to current concerns, not immune to revision, not fully worked out at all timescales. The actual situation is one of careful, productive work on a well-defined topic, with broad predictions that rest on rigorous physics and specific details that continue to be refined. The deep cosmic future is, in this sense, one of the more remarkable theoretical achievements of modern cosmology, and the topic continues to develop through the active engagement of multiple research communities. Tonight, We're going to spend a careful pass on what comes after 100 quadrillion years, because the cosmic future continues for enormously longer than the moment we have explored, and the subsequent epochs are worth understanding in some outline. Now, let's begin with the immediate continuation of the Degenerate Era beyond 100 quadrillion years. The Degenerate Era continues until approximately 10 to the 39th years, which is enormously longer than the moment we have visited. The dominant processes during this extended Degenerate Era include the continued cooling of stellar remnants, the continued ejection of objects from galactic structures through gravitational dynamics, the continued accretion of objects onto the central supermassive black holes, and the eventual decay of protons through processes predicted by some grand unified theories. The proton decay timescale is one of the most important and most uncertain quantities in deep cosmic future cosmology. Some grand unified theories predict that protons can decay through specific quantum mechanical processes with timescales of approximately 10 to the 34th years or longer. Other theoretical frameworks suggest that protons may be entirely stable. The experimental search for proton decay has, as of the present, produced no positive detections, with the current experimental lower limit on the proton lifetime being approximately 10 to the 34th years. What this means is that the proton decay question is one of the most important open issues for the deep cosmic future. If protons decay with timescales of approximately 10 to the 34th years, then the various stellar remnants composed of ordinary matter will gradually evaporate through proton decay over the Degenerate Era. The white dwarfs, the brown dwarfs, the neutron stars composed of ordinary matter will all dissolve into their constituent particles over enormously long timescales. The end of the Degenerate Era will be characterized by the disappearance of all matter except for the black holes that contain matter sealed behind their event horizons. Pause for a moment. If protons are stable, then the various stellar remnants will continue to exist indefinitely through the Degenerate Era. The cooled white dwarfs will remain as black dwarfs forever, with no internal physical process able to dissolve them. The Degenerate Era would, in this scenario, continue much longer than the standard estimates suggest, with the end being defined only by the eventual encounter of remnants with black holes through gravitational dynamics. The Black Hole Era, the fourth of the Adams and Laughlin eras, will begin when only black holes remain as significant cosmic structures. The era will last from approximately 10 to the 39th years until approximately 10 to the 100th years. During this era, the cosmos will be populated exclusively by black holes of various masses, slowly evaporating through Hawking radiation over the enormous timescales we discussed in the insert on Hawking physics. The black holes will evaporate in order of increasing mass. The smallest stellar mass black holes will evaporate first, over approximately 10 to the 67th years. The intermediate mass black holes will follow. The supermassive black holes at the centers of the original galaxies will evaporate last, over approximately 10 to the 93rd years or longer. The Black Hole Era will end when the largest supermassive black holes have completed their evaporation, leaving the cosmos populated only by the products of the Hawking radiation. What surfaces from this is that the Dark Era, the fifth and final of the Adams and Laughlin eras, will begin when the last black holes have evaporated. The era will be characterized by individual particles drifting through essentially empty space, with no significant cosmic structures of any kind remaining. The particles will include photons from the Hawking radiation, neutrinos, electrons, and positrons, and various other quantum mechanical entities. The dark era has no defined end. The cosmos in this state will continue to exist for as long as the underlying physics allows. The cosmic expansion will continue, with the particles becoming progressively more diluted as space stretches. The particle density will approach zero asymptotically, but the cosmos will not strictly end. The dark era is, in this sense, the final state of cosmic structure, but not the final moment of cosmic existence. Walk with me through one specific theoretical question that arises in the dark era. The question of whether the cosmos undergoes a phase transition at extremely long timescales has been considered by various researchers. Some theoretical frameworks suggest that the cosmic vacuum may not be in its absolute lowest energy state, with the possibility of a transition to a lower energy state occurring through quantum tunneling at very long timescales. If such a transition occurs, the resulting bubble of lower energy vacuum would expand at the speed of light, eventually consuming the entire visible cosmos. The probability of such a transition is extraordinarily low. The timescales involved are in the range of 10 to the 10 to the 122nd years or longer, which is enormously longer than even the eventual end of the black hole era. The transition is, in this sense, essentially irrelevant for any practical purposes, but the theoretical possibility exists, and it represents one of the more dramatic possible endings to the cosmic story. No one expects, on first thinking about cosmic deep time, that the cosmic future contains so much additional history beyond even the moment we have explored tonight. No one predicts that the various subsequent eras will play out across timescales that dwarf even the impressive timescale of 100 quadrillion years. Absolutely no one anticipates the way the cosmic story extends across timescales of 10 to the 100th years or more, with substantial cosmic content at each of those timescales. The implications for the broader picture of cosmic existence are substantial. The cosmos contains in its future enormously more time than it has used in its past. The current moment is genuinely early in the cosmic story. The configurations we currently observe are characteristic of only a small fraction of the eventual cosmic history. The vast majority of cosmic time will be characterized by configurations very different from anything we can currently observe. The theoretical work on the deep cosmic future continues to develop. Various researchers are refining the specific predictions for each of the cosmic eras. The role of dark energy in shaping the cosmic future is being studied through ongoing observations of the current cosmic expansion. The proton decay question is being pursued through ongoing experimental searches. The Hawking radiation physics is being refined through theoretical work on the quantum gravity aspects of black hole evaporation. What becomes clear is that the cosmic deep future is a substantial topic of ongoing research, with theoretical refinements continuing to be produced, and with the broad framework being progressively improved. The eventual end of the cosmic story, if there is one, is still being worked out. The various possibilities, including the heat death of the dark era and the speculative vacuum transition scenarios, are being considered as the underlying physics is better understood. Hold this image. The cosmic future continues for enormously longer than the moment we have explored tonight. The Degenerate Era extends to approximately 10 to the 39th years. The Black Hole Era extends to approximately 10 to the 100th years. The Dark Era has no defined end. The cosmos contains in its future far more time than it has used in its past, with the various subsequent eras playing out across timescales that dwarf anything that humans normally consider. The full cosmic story extends far beyond the impressive future epoch we have visited, with substantial cosmic content at every step. For the rest of the night, sit with the cosmos you have just visited, 100 quadrillion years from now, 7 million times older than the present cosmos, deep within the Degenerate Era, but still extraordinarily early relative to the eventual cosmic future. The stelliferous era will have ended 1,000 times earlier than the moment we have explored. The black hole era will not begin for 10 to the 22nd times longer than where we have been. The cosmos at this future time is, in this sense, both extraordinarily distant from now and still just beginning the long, quiet stretch of cosmic deep time. The 5 things we have walked through taken together paint a specific picture. The sky is dark by any human standard of vision. The cosmos is alone with only Milkomeda and the gravitationally bound objects within it remaining accessible. The remaining objects are entirely stellar corpses. The cosmos still produces occasional events through rare merger and disruption processes. The cosmos is poised at an early phase of the Degenerate Era, with the transition to the black hole era still extraordinarily distant. Picture, for a moment, what this future cosmos actually looks like. Milkomeda floats in apparent emptiness, with the cosmic event horizon at a small fraction of its current distance. The galaxy itself is a diffuse cloud of stellar remnants, much less concentrated than current galaxies. Trillions of cooled white dwarfs orbit the central regions. Trillions of brown dwarfs occupy similar orbits. Hundreds of billions of neutron stars and stellar mass black holes are scattered through the system. A single supermassive black hole, by then probably exceeding 1 billion solar masses, sits at the galactic center. The objects move through their gravitational dance, occasionally encountering each other through close passes, occasionally producing rare events that briefly illuminate the otherwise quiet cosmos. The view from inside Milkomeda at that future time is one of pervasive darkness, occasionally punctuated by extraordinarily faint sources. The cooled white dwarfs emit at temperatures only slightly above the cosmic background, with their thermal radiation being in the radio and microwave bands rather than the visible. The neutron stars and black holes are essentially invisible to anything other than gravitational detection. The brown dwarfs emit faintly in the infrared. The occasional merger-produced star burns at low temperatures in some specific location for trillions of years before joining the cooling remnant population. The total light output of the galaxy is many orders of magnitude lower than the current Milky Way luminosity. Slowly, the camera in your imagination drifts outward. It leaves the room where you are sitting. It rises above the building, above the city, above the planet. It travels outward through the solar system, through the galaxy, through the local group. It pushes forward in time, accelerating through the stelliferous era. The bright young galaxies fade. The middle-aged galaxies of the present moment give way to older galaxies, then to the dim galaxies of the late stelliferous era, then to the cosmic structure of the early Degenerate Era. The cosmos becomes progressively quieter, with fewer active stars producing fewer photons. The camera continues forward in time. It approaches the moment we have explored tonight. Milkomeda appears in the field, a diffuse cloud of stellar remnants floating in apparent emptiness. The cosmos beyond Milkomeda has been carried beyond the cosmic event horizon with only the dim background of cooled cosmic radiation remaining. The local galactic structure contains the trillions of objects we have discussed. each one a specific physical entity with its own history and its own future. The camera sees the cosmic structure at 100 quadrillion years, observes its quiet dynamics, and recognizes it as the cosmos that has emerged from the present cosmos through 100 quadrillion years of continuous physical evolution. The camera turns around and begins the long drift back, past the future moment we have explored, backward through the Degenerate Era, backward through the end of the Stelliferous Era, backward through the long middle stretches of stellar activity, backward through the active era of galaxy formation, backward through the cosmic dawn, backward through the cosmic microwave background, backward through the early universe, all the way back to the present moment. The cosmos, as we observe it, now appears, with its rich structure and its active stellar populations and its observable cosmic web. The camera approaches the present cosmos from this temporal direction, past the galaxies of the cosmic web, past the local group, past the galaxy, past the solar system, past the planet, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You are still here. The version of you in this room on this night is alive in the present cosmos. The cosmos you currently inhabit will continue to exist in some form for enormously longer than the moment we have visited tonight. The eventual future is genuinely strange. The future cosmos is genuinely quiet. The future cosmic environment is genuinely different from the cosmic environment you currently inhabit. But the future is also extraordinarily distant in time, and the present cosmos is, by every available measurement, what you have available to you right now. What this means for how you experience the present cosmos is subtle. The cosmos around you is currently in the active early phase of cosmic history. The stars are still burning, the galaxies are still visible. The cosmic web is still accessible to our instruments. The cosmic moment you are living through is, in this sense, one of the more empirically rich moments in the long cosmic story. The deep cosmic future will be quieter, but the present cosmos is genuinely beautiful and accessible. The cosmos has, in this sense, given you a particular cosmic moment. You are alive during a phase when the cosmic structure is still rich and observable. You are alive during a phase when stellar formation is still occurring, when galaxies are still active, when the cosmic web is still mappable. Future generations of cosmic observers, separated from you by hundreds of billions of years or more, will inherit a much quieter cosmos, with much less observational richness. The current cosmic moment is a particularly favorable time for the kind of empirical work that produces the rich cosmological understanding we currently enjoy. There is no need to hold all of this in your mind. The 5 things will keep their shape, whether you remember the details or not. The deep cosmic future will unfold according to the well-understood physical laws regardless of whether anyone is around to observe it. The Stelliferous Era will end at its expected time. The Degenerate Era will play out across enormous timescales. The Black Hole Era and the Dark Era will eventually follow. The cosmic story will continue with or without observers. The cosmos that contains your sleeping body is the present cosmos, with all its current richness and all its current activity. The future cosmos we have explored tonight is genuinely real, but it is also genuinely distant in time. The present is what you have. The present is what is here. The present cosmos is, in this sense, both a temporary configuration and a genuinely valuable one. Whatever observations you make of the cosmos in your lifetime are observations of a configuration that will not be available to any future observer in your region of space. Sleep can come whenever it wants now. The story has done its work. The cosmos at 100 quadrillion years is out there in the cosmic future, slowly evolving through its long, quiet processes. The cosmos now, in this room, on this planet, in this galaxy, is here, rich and active and accessible. Both cosmoses are real. Both are part of the same continuous cosmic story. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.